This video we're going to talk about section 6.1 in our books on antiderivatives. So if capital F prime of x is equal to little f of x, then capital F of x is an antiderivative of little f of x. So notice that's just an antiderivative. I'm not saying it's the antiderivative. So for example, capital F of x equals x squared is an antiderivative of little f of x equals 2x because the derivative of capital F prime would be 2x. But so are capital G of x is equal to x squared plus 1 because the derivative of x squared is 2x and the derivative of 1 is 0. And also capital H of x equals x squared minus 11 because, again, the derivative of x squared is 2x and the derivative of negative 11 is 0. So capital G, capital H, capital F all have as their derivatives 2x. So they are each considered an antiderivative of little f of x equals 2x. So capital F of x equals x squared plus c, where c is any constant, is a family of functions which are all antiderivatives of little f of x equals g of x. We'll sometimes call capital F of x the general antiderivative. So it represents all of those. So let's take a look at how we can get the graph of f from the graph of its derivative. So we change notation now, so we're not using capital F and little f, we're using little f prime and little f. So little f of x, if we see the graph of f prime of x is this horizontal line y equals 3, then we know that its antiderivative could be 3x plus any constant, because the derivative of 3x is 3 and the derivative of a constant is 0. So out of all those choices for C, sketch the graph of of f of x if f of 0 equals 0. So if f of 0 equals 0, that means 0 is going to be 3 times 0 plus c. That means the c is going to be 0, and that means our f of x is going to be just 3x with a y-intercept of 0. So that would mean we would start at 0, we can rise 3, run 1, and we would get our f of x would look something like that. So there's one possible f of x. Now if f of 0 is 2, then that means that for our f of x equals 3x plus c, when we plug in 0 for the x, we're going to get 2 for f of 0. And so that means that the c would be 2, and that means what we're going to graph is 3x plus 2. And so we're going to start at 2, and again have a slope of 3, and so we would get something that looks like that for our f of x. Notice that for these different choices of c, what we get are translations, vertical translations of each other. They're still the same basic graph. They're still straight lines with slope 3, but they just have different y-intercepts. They're vertical translations of each other. Okay, now we're going to get a little bit more complicated here. So now we see that if f is continuous and f of 0 is 0, can we piece together the graph of f of x from this piecewise derivative? So first let's look at the part of the graph that kind of looks like this, because that's the part where we know what f of 0 is going to be. So on this part, we have a line that has slope of negative 1. So for that little piece of it, we can see that f prime of x is going to be negative x. So that would mean that an antiderivative, or the general antiderivative of f of x, Can you see what that would be? It's going to be a negative 1/2 x squared plus some kind of constant. We can check that because its derivative, if we differentiate x squared, that 2 times the negative 1/2 will cancel, and we'll just get negative x, and the derivative of the constant is 0. So if we're going to use the fact that f of 0 is equal to 0, that means that we'll get 0 for f when we plug in 0 for x, and that's going to tell us that c is equal to 0. So far, we've got that f of x is going to be negative 1/2 x squared plus 0. So that part of it is going to work from negative 2 to 2. So let's see. At 0, we have 0. When we plug in 2, f of 2 is going to be 2 squared is 4 times negative 1/2 is negative 2. So at 2, we're going to be at negative 2. F of negative 2 is going to be negative 2 squared is 4 times negative 1/2 is also negative 2. So we're also going to be there. And this is going to be a parabola that opens down. So far, this is what we know about our graph f of x. Now it changes here. Now on this piece of the graph here, we have a horizontal line of 2. That is, our f prime of x is equal to 2. So the general antiderivative of 2 is going to be 2x, because that's derivative is going to be 2, plus some kind of constant. Well, we want, because we're looking for a continuous f of x, we want, when we try to connect our graph here at x equals negative 2, we want this part of the curve to connect with the part that we already have. So we're going to say that at f of negative 2, this is going to be negative 2 squared. Well, we know it's going to be a negative 2. So that becomes the part that we're going to plug in here. F is going to be negative 2 when the x is negative 2, and what value of c will give us that? So 2 times negative 2 is negative 4. So that means we want c to be a positive 2. So our f of x is going to be f of x equals 2x plus 2. Now, that's what it would actually be. We can kind of tell right here. I mean, we didn't really have to do all that to know if it's continuous, it's got to connect. And we can also see that it has to have a slope of 2. And we're going to continue this until we get to an x value of negative 4. So we could also have said, well, if the slope is 2, we can go down 2 over 1 and connect that, and down another 2 over 1 and connect to there. That would be just kind of the visual representation. Or we could have said, we know we're going to end up at negative 4, that if we plug in the negative 4 here, we'll get 2 times negative 4 plus 2 will be negative 8 plus 2 is negative 6. So there's 1, 2, 3, 4, 5. There's our negative 6 right there. A couple different ways of doing that. Let's try the same ideas to get the other part. Now, over here, we can see that our f prime of x is negative 2. So that means that f of x is going to be negative 2x plus c. Now we could just say, well, I know that right here, because it's got to be continuous, I've got to start here, and we can go, we know we're going to have a slope of negative 2, so we can go down 2 over 1, down 2 over 1, and we're going to end up right there, also at negative 6. We could also have used this to figure out what is that going to be at 2. And 2 squared is 4 times negative a half is negative 2. So that would have told us here that the f value, the y value, is going to be negative 2 when the x is positive 2. And that would tell us, let's see, negative 2 times 2 is negative 4. Add that over is going to be, c is going to be positive 2. And so we would have gotten f of x is going to be negative 2x plus 2. We could have plugged in our x value of 4 to see where we're going to end up, and that negative 2 times 4 plus 2 is negative 8 plus 2 is negative 6, and that's the negative 6 that we're going to end up at. Okay, kind of interesting pieces to put together there. We'll be doing more of that kind of stuff in the future. So, suppose velocity v of t is given by this graph you see in yellow, a couple of straight line segments. The position at t equals 1 depends on where you start. So, if we started at 1, then we can see that our change of position, that is the area that we get under the curve from 0 to 1, is going to be this part right there. And that area is 1/2 base times height, which is going to be 1. So the area of that blue shaded triangle is 1. And that is going to be our net change in position from t equals 0 to t equals 1. Because that's below the x-axis, we're going to think of that as being a negative 1. So from our starting position, we're going to get negative 1 to the left. Another way of thinking of this is that we could say that the integral from 0 to 1 of v of t is the integral from 0 to 1 of s prime of t, because velocity is the derivative of position. An antiderivative of s prime is s of t from 0 to 1, and that's going to be s of 1 plus s of, or minus rather, s of 0. Oops. So adding that s of 0 to the other side, we'll get that s of 1 is going to be our starting value, s of 0, plus there's our net change in position that we were talking about. So if we started at 0 and our displacement or net change in position was negative 1, that means that s of 1 in this case would be a negative 1. Similarly, if we started at 5, then our position at time 1 would be 1 to the left, would have been 4. And if we started at negative 2, our position at time 1 would be a negative 3, 1 to the left. Okay. So compute antiderivatives using definite integrals. Using that idea we just talked about in velocity, we can generalize that beyond just velocity to any kind of function. Since the integral from a to b of f prime of x is f of b minus f of a, if we know f of a and something about f prime of x, we can, that is like we know its graph or its equation, we can find f of b. Again, what we're going to do is we're going to say that f of b is going to be, we're going to add this to the other side. It's going to be f of a plus the integral from a to b of that f prime of x. So if we have a graph, we can use an area argument. If we have an equation, we can try to do it more analytically or algebraically. Okay, let's see what we can do here. We have here the graph of f prime in yellow, and we know that f of 0 is 100. can we find f of 10? Well, the idea is that f of 10 is going to be f of 0 plus the integral from 0 to 10 of f prime of x. So f of 0 we know is 100, and we can make an area argument to find the integral from 0 to 10 of f prime. So we can look at this triangle and know that that's going to be 1/2 base times height. Oops, I bumped the wrong thing with my hand. So using our area argument here, we're going to say that that's 1/2 base, which is 10, times the height, which is 20. 20. So that's going to be 100. So we're going to add that integral from 0 to 10, which is 100, to the f of 0, which was 100, and that's going to be 200. Similarly, f of 20 is going to be f of 0 plus the integral from 0 to 20 of f prime of x. And we know the f of 0 is 100, and the integral from 0 to 20 of f prime, we can do this bigger triangle. So we're now going to, let me see if I can erase that dotted line without destroying everything. Not very well. I'm going to reconstruct those parts of it there. So we're now talking about the area of this whole piece here. So that's going to be 1/2 its base, which is now 20, times its height, which is 20. And so that's going to be 200. And so that's going to make f of 20 be 300. And likewise, f of 30 is going to be f of 0 plus the integral from 0 to 30 of f prime of x. And that's going to be 100. There's our f of 0. And now what we want is f of, the integral from 0 to 30 is going to be the triangle that we just got. There's, that much is 200. And then we're going to also include this, but now that's below the x-axis, so that's going to count as a negative. So 1/2 base times height there is 1/2 the 10 times 10. So that's going to be 50, but that's going to be a negative. So we're going to get the 200 that we had minus that 50 is going to be 150. And so that is going to make f of 30 be 250. Okay, now let's plot those points while we've got them. So we know that f of 0 we said was 100, and we found that f of 10 is 200, f of 20 is 300, and f of 30 is 250. So that's going to be right there. Now, before we connect these, let's use what we know about increasing, decreasing, concave up, concave down. So we're graphing here, we're trying to graph y equals f of x. This graph in yellow is the derivative. So we know that f is going to be increasing when its derivative is positive. And we can see that's going to be between 0 and 20. Now, f prime is positive. We wouldn't include the 0 and the 20, but f increasing, we will include both the 0 and the 20. So f is going to increase on the interval from 0 to 20. Similarly, when the derivative is negative, the function f is going to be decreasing, and that's going to be from 20 to 30, where we see that graph of the yellow f prime below the x-axis. F will be concave up when our second derivative is positive, which is going to be where the derivative graph is increasing. So that's going to be along that part from 0 to 10, and also on that part from 25 to 30. F will be concave down when the second derivative is negative, which is going to be when the first derivative is decreasing, and that's going to be from 10 to 25. So we will have relative extrema, relative mins and relative maxes, when the derivative changes sign, and we can see that it's going to change from positive to negative at x equals 20. And we said that when x is 20, the y value is 300. So 300 is going to be a relative maximum. We get inflection points when the second derivative changes sign, and we can see from our work here that's going to be at 10, where it's going to change from concave up to concave down, and again at 25, where it changes from concave down back to concave up. We know the coordinates of those points from the work we did earlier. At 10, we know the y-coordinate is 200, and at 25, I guess we don't know that one, but we can figure it out. I think at 25, it looks like it's going to be, oh, we do know, no, that was 30. At 25, it's going to be, what will that be? So we are going to be subtracting off 25 from the 300, so I think that's going to be 275. Okay, so let's see. We also know that if we were going to, for the shape, well, we can get it there, I think. So we know that our graph is going to be increasing and concave up from 0 to 10. So it's going to do something like that. Then at 10, it's going to switch to being concave down, but it's going to continue to increase until we get to 20. Then it's going to decrease, but stay concave down until we get to, I should have said 25. So let me back that up a little bit. So at 25, we said it was going to be 275. So that's going to be right in there. So it's going to be decreasing and concave down. And then from 25 to 30, it's going to be decreasing but concave up. So it's going to look something like that. All right. So let's look at a couple other examples using this idea of connecting the values of a function to the derivative. So let's say here that our calculator is going to be okay. Calculator. So let's say that f prime of x is x cosine x, and that f of 0 is equal to 5. And armed with that knowledge in our calculator, can we then find what is f of pi over 4? So again, what we're trying to do is say that f of pi over 4 is going to be f of 0, because we know what that is, plus the integral from 0 to pi over 4 of f prime of x. And so our f of pi over 4 is going to be f of 0, which we said was 5. And now we're going to get the integral from 0 to pi over 4 of x cosine x dx. Now we don't know how to do this integral, but we're going to use our calculator for it. So we can, and to our calculator, go 5 plus, and then our fn integrate, and we'll go from 0 to pi over 4 of x cosine of x. And if you do that, I believe you should get 5.262. Okay, so there's a calculator active problem using this same idea. Now, even maybe a little different one. This is like, say, page 323, number 14 in our book. I'm going to do an abbreviated version of that. So we're just going to estimate what is f of 2. And we're going to say that we know that f of 0 is equal to 50. And we have a table of values with some values of x and f prime. And we'll just say that we know 0 and 2. There's more on the actual problem in the book, but we're just going to do a limited example of that right now. So the idea is we know that f of 2 is going to be f of 0 plus the integral from 0 to 2 of f prime of x dx. Now we know that f of 0 is given to us as 50, and our challenge with this little bit of information is how can we approximate this integral from 0 to 2 of f prime. And so let's do, we're not really given much direction, so let's think of maybe a Riemann sum. And let's just choose maybe a right Riemann sum. So if we do a right Riemann sum, then we can see we're going to have just one rectangle between 0 and 2. And so we can say this integral from 0 to 2 of f prime of x is going to be approximately equal to, and we're going to use the 15 as the height of that rectangle, and 2 minus 0 is going to be the base of that rectangle, and so that will be 30. And so we can say that an approximation to f of 2 would be the f of 0 plus our estimate of that integral from 0 to 2 of f prime of x. And so we'll call that, it should be an 80. Okay, very good.